Hello everyone. In our past videos, we discussed PLCs and we got to know that a PLC or a programmable logic controller forms a very fundamental component of control systems, especially where we have complex systems or complex processes, but we also found that we can utilize PLCs to control simple circuits in the industry. And so we looked at how you can program a PLC. We looked at a number of softwares, a number of companies that own softwares and the PLCs. So we looked at the Siemens, we looked at Omron, we looked at Schneider, and so on and so forth. Now, one of the ways of programming a PLC is using ladder logic. We also said we have structured text, we have instruction list, we said we have function, block diagrams, and so on and so on and so forth. So ladder logic is among them, and we are saying it's a graphical programming language widely used in industrial automation to control machines and processes. It is designed to be intuitive for electricians and engineers familiar with electrical ladder diagrams due to its similar structure. So now we look at the key features of the ladder logic. We find that ladder logic programs resemble a ladder with horizontal rungs and two vertical rails. The left rail represents the inputs to the program, typically from sensors, switches, and other control devices. Then these can be shown as contacts on the rungs. Now, the right rail represents the outputs of the program, which control actuators, relays, or other devices. You might have at the right rail, you might have a motor, you might have another coil, for example, a relay, which switches on a motor. So you can have a number of output devices on the right rail of the ladder logic. These are represented as coils on the rungs. As we have said, we can have relay coils, and that's the basic one we can find in ladder logic. The rungs contain the program logic defining how the inputs should influence the outputs using instructions and logic gates. So we shall find that logic gates also form a strong foundation on understanding how ladder logic operates. So you will see that we shall have the AND, the OR, the NOR, the NAND, XOR, and so on and so forth. So let's look at the ladder logic and the symbols. You can see we have a normally open relay contact. So this can be also called an NO contact or just a normally open. This is normally open like the way you see the normally open push button in the motor control systems, where you have a push button that starts the motor, and then you have another button that stops the motor, which is a normally closed. So we call it an NC. So this is NC push button contact to, of course, give you a hint on what NC or normally closed contact behaves or looks like. And this is the relay coil, but we can also have it as just brackets or an oval that has an opening on top and at the bottom. Then these lines, the horizontal lines, are showing the path followed by the signal. Then there are a number of others. We have the indicator lamp. This is the symbol. Then the fuse. This is the overload heater. Then the three-phase motor. Then you have the negative transition sensing contact. Looks like this. The negated coil, if you have a coil and you negate it, this is the symbol. Then the set latch coil, you have the output with the S in the middle. Then, of course, the reset would be having R. Then this output or coil with a P informs you that this is a positive transition sensing coil. So, benefits of ladder logic is that it is visual and intuitive in a way that, of course, you look at it and simulate the program or the process and see it working. In other words, you can look at it and know the program is running or not. The graphical representation makes it easier to understand the control flow compared to text-based programming language. So it is easy also to troubleshoot by tracing the logic through the runs and observing the status of contacts. You are able to know where the problem is. Then it is suitable for industrial applications. Ladder logic is well suited for controlling physical systems with real-world inputs and outputs that are common in industrial settings. So if you want really to understand the ladder logic, you need to also get this kind of analogy. So you imagine a physical ladder where each rung represents a control condition. So those two vertical or two other lines where these rungs are connected, we call them rails or power rails. So you have the left power rail, you have the right power rail. Now to activate, for example, a light bulb, which is an output, you might need two switches. So these two switches, we take them as inputs on the same rung to be turned on. That is a closed contact. When you turn them on, then that means you have made a closed contact. Simultaneously, like an AND gate, we have already said that ladder logic, for you to understand it, you need to also understand the basics of logic gates. And a NAND gate is one of the basic ones that tells you that the output is only going to be high only and only if all the inputs are high. So this is equivalent to connecting your switches in series to turn on a bulb and with, of course, a battery as a source. So when you connect your switches in series, you are actually operating on AND gate analogy. Then we are saying this is also similar to how ladder logic uses contacts and coils to represent inputs, outputs, and the logic controlling them. So you might have two contacts on one rung, and those two contacts on the same rung are going to be operating on an AND gate analogy. So when all of them are high, that's when the output is going to be high. Then the common components in ladder logic, we shall see, as we have already said, we have contacts. These represent the program's inputs from sensors, switches, and they come majorly in two types. We have the normally open contact and the normally closed contact. So the normally open only conducts when the input is active. That is when you close it. Then normally closed contact will conduct by default. So this one, this normally open is actually not closed but is open. So you have to first close it and then it is able to conduct. Then the normally closed by default it is always closed and opens when you de-energize that kind of input. So when the input is active, you will see that it actually de-energizes and opens the contacts, and then you are able to either actually that now you will be able to either stop or start the system depending on the configuration you would have you started with. or the design that you use. Because, for example, in the motors, you will see that it is a common habit or a common culture to put, for example, the start push button to be in normally open position, then the stop or emergency stops buttons or push buttons are always connected in normally closed uh, kind of a scenario, so that when one comes and pushes on it, then you open the contacts and you de-energize the coil, and then you stop the motors or you stop the system. Then we have also other components that are within the ladder logic. The coils represent the program's outputs and control devices, like we already said. The instructions define the logic within the ranks to control the outputs based on the inputs. These can involve basic logic gates, the AND or not, and so on and so forth. So now the logic gates and ladder logic, we said they are analogous to each other, and we are saying these gates perform simple operations on input signals with a 0 or 1 to produce an output signal. Then we are saying ladder logic programs can implement the functionality of logic gates using contacts and calls arranged in specific ways on the rungs. So now we are going to look at an example, but now what we are going to do in the next video, we are going to discuss how you can actually create an AND gate, a NOR, NOT, XOR function using ladder logic. Follow us in the next lecture for you to be able to understand that.